So today we're going to look at calculating probabilities in multi-step experiments when you have dependent probability, where you're calculating without replacement. But before we can get to that level of complexity, there's a few ideas we got to make sure we have ahead of time. The first is this basic formula that you see here, which is just how you calculate the probability of any event. That's going to be the number of favorable outcomes divided by the number of total outcomes. We've been seeing this over and over again in probabilities so far. It's pretty straightforward once you get the hang of it, right? You have an example like, let's say you're looking at a bag of marbles, and in that bag of marbles, let's say you've got 100 total marbles, right? And of them, 20 are blue, 30 are black, 10 are white, and 40 are green. Then in order to calculate the probability of getting one white marble, if I pick one marble at random, then I say, well, what are the total number of favorable outcomes? Let me divide that by the total number of possible outcomes. And in this case here, let me make sure I get in this case here, I've got 10 white marbles. Those are my 10 favorable outcomes. And if I add all these together, 20 plus 30 plus 10 plus 40, I get 100 possible outcomes. So my probability calculation that I'll have to do is just going to be 10. Actually, let's do this with a paintbrush here, so you can, and I'll make it nice bright red for you. I'm going to do 10 is the total number of favorable outcomes. Those are the white marbles. And I divide that by the number of total possible outcomes, which is going to be 100 here. And then once I have that basic fraction, I'm going to reduce it. So 10 over 100, I'm going to reduce to 1 over 10. And since it's probability, I can express it a number of different ways. Here, the probability of white could be expressed as 1 over 10. I could also express it as 0.1, which would be the decimal equivalent of the same thing, or 10%. Any of those would be a correct answer here, right? And so that's your basic probability. That's just your favorable outcomes divided by your total possible outcomes. The next concept we want to make sure we have in store before we get into the more complicated stuff is this idea that if you're dealing with a multi-step experiment, that means where you perform one step, you see what happened, and then you perform a second step, that the way you calculate the probability of that is the probability of the first outcome times the probability of the second outcome in that second step. Okay, and so let's do a little example of that. Let's say I'm rolling a die here. And I roll the die first time, and I look and I see what I get. I observe the result. And then I roll it a second time, and I look at the result then. So if I wanted to calculate the probability that I rolled a 3 the first time on the first roll, and then a 5 on the second roll, or another way I'd write this is just what is the probability of 3 and then 5, that's just how we write the same question, then I would calculate, well, what's the probability of getting a 3 the first time around, and what's the probability of getting a 5 on that second roll, and then I'm going to multiply those two together, right? Well, the probability of getting a 3 on a regular 6-sided die, there's one favorable outcome, that's the 3, and 6 possible outcomes, those are all outcomes including the 3 in there. That's 1 out of 6. Probability of getting a 5, it's a different outcome that I'm thinking of here, but it's the same probability, right? There's 1 5 and there's 6 faces on the die. So to get the probability of rolling a 3 and then a 5, I would do 1/6 times 1/6, which would give me 1 out of 36. And again, you could express that as a percentage, as a decimal, right? But 1 out of 36 is the most exact way because this doesn't come out so easily as a nice decimal or as a nice percentage. So 1 out of 36 is the best way to express this. Now, you might be looking at this and saying, well, I know we've looked at dice questions before, and if you're rolling a 3 and a 5, then you're getting an 8, right? If I play a game, I'm getting an 8 with a 3 and a 5. And I thought the probability of getting an 8 was actually a lot higher than 1 out of 36. You're right, but look here, what we're not observing what the sum is, what the total is. We're specifically just observing what is the probability of getting a 3 the first time and a 5 the second time. That means we're not going to include in our total here getting a 4 the first time and a 4 the second time, right? You wouldn't include a 2 and then a 6 either, even though those all contribute to getting an 8. So that's why your probability here, 1 out of 36, is a lot lower than the probability of getting an 8. We don't aren't calculating 8, we're just calculating 3 the first time, 5 the second time. Nowhere in this question does it say calculate the probability of getting a sum of 8. That's a separate question. Okay, so in this case here, it's just probability of the first step times probability of the second step. Now, where this gets a little more complicated is if we incorporate the most recent idea we've talked about, which is the difference between independent events and dependent events. Now, an independent event in probability is when you have multiple steps. The first step might be something like flipping a coin. The second step could be spinning a spinner, right? The important thing is in independent events, what happens in the first step of the experiment doesn't affect what happens in the second one, right? So that's why I gave the example of flipping a coin and spinning a spinner. When you flip the coin, that doesn't affect what's going to happen with the spinner in the second step of the experiment. On the other hand, dependent events works the opposite way. In dependent events, whatever happened in the first step of your experiment is actually going to affect to some degree what happens in the second. And we'll see how to calculate that in a second. It's a little more complicated. You'll see that we'll often refer to independent events as events with replacement. You'll see why in a second. Whereas dependent events we'll sometimes talk about as being events without replacement, and specifically why we'll show in a second. So if you look here, here's an example of independent events. All right, this is my same bag of marbles. It's still got 100 marbles. There's still 20 blue, 30 black, 10 white, 40 green. If I draw a marble at random, I'll look and see what color it is. And then I put the marble back in. This is why you see we talk about independent events as being with replacement. I'm replacing the marble back in the bag. If I put the marble back in the bag, then I'm still on my second step. I'm still dealing with a bag of 100 marbles. I'm still going to take one out. And the probability of getting white on the first draw isn't going to affect what happens in the second draw. Because if I pull out a marble, I look at it, whatever color it is, maybe it's white, maybe it's not, I'm putting that marble back in the bag. Then I'm drawing a second marble, or I'm drawing a marble out of the bag a second time, and whatever happens on the second time isn't going to be affected by what happened the first time, right? So the calculations for that are pretty easy. If you're dealing with dependent events, that means the second step is affected by what happened in the first step, then it's not quite the same. See, I still start out in my first step with a bag of 100 marbles. And when I draw one marble out, I look at its color. If I do not put it back in the bag, if I don't replace it in the bag, then now for the second time when I draw a marble, there aren't 100 marbles in the bag. There's 99 marbles in the bag. And if I took a white marble out the first time, and the probability of that, is we already saw, that's 1 out of 10, then I'm not putting that white marble back in. So instead of the next step being 1 out of 10, we'll see that it would actually be 9 out of 99. Now, I'll explain why that is. We'll do the example in more depth in a second. But just so you understand, if you're not putting the marble back in the bag, then the second step of the experiment is affected by whatever marble you didn't put back in there, right? Whatever color that is, since it didn't go back in, that's going to affect the composition of your outcomes in here. Okay, so let's do the actual examples to illustrate. Here, this example, since I'm putting it back in the bag, this is with replacement, this is independent probability. If you read this here, you draw one marble at random, you observe its color, you put it back in the bag, you draw one marble at random again, you observe its color. The second marble I'm taking out, not affected by what happened in the first step. So each of these steps, the probability is going to be independent of each other. What's the probability of getting a white marble on the first draw? Well, I got 10 white marbles, like we saw in our first example today, out of a total of 100. So I do favorable outcomes over total outcomes, and that's 10 over 100. And then, since this is a two-step experiment, I'm going to multiply that by the probability of the second step. Since I've put my marble back in, I've still got, on my second step, I've still got 100 possible outcomes. And of those 100 outcomes, 10 of them are white marbles. So the probability of getting a white marble on the second step is still exactly the same, 10 out of 100. So I would simplify these. 10 out of 100 becomes 1 over 10. This becomes 1 over 10. I'd multiply them together, and I would end up getting, you could even do it this way, right? Cross out the zeros like that. You would end up with a total probability of getting white twice in a row in a circumstance like this is 1% or 0.01, or as I'm writing it here, 1 over 100. But if you look at this example here, it's going to be different. Whoops, let me get this in the screen for you here. In this example here, still got my bag of marbles, still 100 marbles, still 20 blue, 30 black, 10 white, 40 green. I draw one marble at random and I observe its color, but I don't put it back in the bag. Okay, so let's do that first step first. I'm saying I'm drawing a marble out of my bag of 100 marbles, so the total possible outcomes are 100. What is the probability that this first step gives me a white marble? Well, there's 10 white marbles, so the probability of that is 10 out of 100. But then, on my second step, I've taken a marble out of this bag, and it's not in there anymore. So the total number of possible outcomes isn't 100. There aren't 100 marbles. There's only 99 marbles. And if I'm assuming, and this is kind of the hardest idea to get your head around in this bit, if I'm assuming that when I took a marble out the first time that it was white, it means that now the composition of marbles in this bag is 20 blue marbles, they're all still in there, 30 black marbles, not 10, but now it's gone down to 9 because I took that white marble out, I didn't put it back, and 40 green. So I have 99 total marbles, but only 9 of them are white. So the probability of getting white a second time is now 9 out of 99. I'm still going to multiply these two to get my final answer. I got to say, all right, well, I can reduce these fractions a little bit. Let me cross out these zeros here. This is 1 out of 10. 9 out of 99, I could actually reduce this fraction to 1 out of 11. So now I have 1 out of 10 times 1 out of 11, and I end up getting an answer, not 1 out of 100 like we just saw, but 1 out of 110. That's less than 1%. That's less likely. And if you think of it, compared to the example we did before, where we got 1 out of 100 as an answer, it makes sense that if you take that white marble out randomly and you don't put it back in, the chances of getting 2 white marbles in a row are going to be less than if you had put the white marble back in, because there's fewer white marbles that you could end up picking. So that's how you calculate a situation involving dependent probability, where it's without replacement. You don't put it back in the bag, and you have multiple steps. You calculate the probability of the first step, you calculate this dependent probability in that second step, and you multiply them together to get your final answer.